hemos tenido la oportunidad en esta, yo no sé, algunos a lo mejor no lo sabéis, pero 2 o 3 veces al año solemos aprovechar que tenemos la oportunidad de tener ponentes prestigiosos, pues para, en un acuerdo de cooperación que tenemos entre mi centro de investigación, Indea Energía y la EOI, pues de aprovechar esas visitas o esas estancias para que vengan aquí a contaros cosas, y hoy ha sido el caso, ¿no? Os voy a decir que la verdad es que es un honor, y yo creo que vais a ver que es una suerte que hoy tengamos aquí. Ya le voy a presentar directamente al profesor Aldo Steinfeld, que aunque no lo creáis me está entendiendo muy bien, porque entiende español perfectamente. Y bueno, pues el profesor Aldo Steinfeld, que es el miembro del Consejo Científico de Indea Energía, estaba hoy aquí, y de ahí que deprisa y corriendo hayamos hecho la organización de este evento, porque creemos que el tema que os puede presentar aquí os aseguro que es de candente actualidad. El profesor Aldo Steinfeld es en la actualidad, y ya desde hace unos cuantos años, es full professor, es decir, catedrático de una de las escuelas de ingeniería más prestigiosas del mundo, que es el ETH de Zurich, en Suiza. Dentro de esa universidad, él es el responsable del departamento o del programa, no sé cuál es la definición, de Renewable Energy Carriers, que más o menos pues sería de vectores energéticos renovables, y además simultanea esa responsabilidad con la dirección del laboratorio o del departamento de tecnología solar del Paul Scherrer Institute, PSI, que es el centro o el laboratorio nacional de investigación energética en Suiza, que está muy cerca de Zurich, ¿no? El doctor Steinfeld hizo su tesis doctoral ya en temas relacionados con los combustibles solares. Él, aunque es ingeniero aeronáutico, ha hecho su tesis doctoral ya en temas energéticos en la Universidad de Minnesota, yo creo que por el año 1989. Posteriormente estuvo durante un periodo de tiempo trabajando en el Instituto Weizmann en Israel, también en líneas muy punteras, sobre todo en lo que tiene que ver con combustibles solares. Y bueno, pues en la actualidad dirige muchísimas líneas de investigación que tienen que ver con la química solar, la investigación en la producción de combustibles solares y todo las oportunidades que se pueden abrir en ese tema. Entonces, bueno, es un poco a lo que nos va a contar hoy. Entonces, por favor, Aldo, cuando quieras.
Bueno, muy bien. Gracias, Manuel, por la introducción. Buenas tardes a todos, y voy a cambiar el idioma. No puedo dar una charla en español, me tranco. Tendríamos que estar hasta la mitad de la noche si lo hago en español. Entonces cambio en inglés y lo puedo hacer más rápido. But I will talk slowly and vocalize, so I believe you should be able to follow me. And if you don't, stop me and ask me, and I'll try to answer in Spanish. So the title of my talk, you see it over there: Liquid Fuels from Water, CO2 and Solar Energy. So this is the recipe, and with the ingredients: sunlight, water, CO2, to produce fuels. Fuels that can be stored for long periods of time, fuels that can be transported over long distances, so that we can fuel our cars, and we can drive our cars also on a rainy day in Madrid, and we will be driving with solar energy. We are especially interested in this mixture. We call it syngas, mixture of hydrogen and CO. Why is that? Because this is the precursor for conventional liquid hydrocarbon fuels such as diesel, kerosene, jet fuel, and also some alternative liquid fuels such as methanol. When we use these hydrocarbon fuels in our cars, in our airplanes, we will be emitting water and CO2, And we will have to take care that these two guys come back into our recipe to close the material cycle. Closing the material cycle is the key issue when we talk about a sustainable energy utilization. You have to make sure the material cycle is closed. You may recognize this photograph. This is the PS10 and PS20 in Andalusia, Seville. How many of you are not familiar with this type of technology? Are you all familiar?
They should.
Then I will skip. The important thing I want to mention here when I'm showing this photograph is that solar chemical technologies, that is the topic of my talk today, are not as developed as solar power technologies, but they will make use of the same infrastructure. We will make use of the same heliostat field tracking the sun and concentrated the solar energy. We'll make use of the same tower. However, we'll remove the boiler that is here on top of the tower and we'll place our solar reactor. And today we'll talk about what is the solar reactor, what is the process that we will do here on top of the tower. Perhaps when we talk about fuels, we come right away into one attractive fuel. This is hydrogen. And when we talk about thermochemical production of hydrogen, the most conceptually simple process would be the direct splitting of water into its elements, hydrogen and oxygen. However, the direct splitting, usually called the thermolysis, is not as simple as it appears. Part of the reason is you can see the very high temperatures required. The delta G of the reaction goes to 0 at temperatures above 4,000 K. Further complication arises from the fact that at high temperatures, water dissociates into hydrogen and oxygen and other species, as you can see here in the equilibrium composition diagram at 1 bar. For example, at 3,000 K, we will have about 30% dissociation of water into hydrogen and oxygen, but we'll see other species, for example, monoatomic hydrogen, monoatomic oxygen, OH. These are undesired species. We don't like them. However, the most difficult part of doing the direct thermolysis of water is the need to separate hydrogen and oxygen at high temperatures in order to avoid ending up with an explosive mixture at ambient temperature. And the separation of these two guys, hydrogen and oxygen, at high temperature, it's a very difficult issue. There is a way of bypassing the problem of separation, and this is by making use of thermochemical cycles. And I'm going to be focusing on a two-step thermochemical cycle, and here is the diagram of this cycle. In the first step, a metal oxide, which is denoted by MOX, is thermally reduced and oxygen is set free. This is a highly endothermic step that proceeds at high temperatures, and concentrated solar energy is the source of this high temperature processing. In the second step, the metal oxide reacts either with water or CO2 to give hydrogen and CO, our zinc gas mixture. And the original metal oxide is reformed and recycled to the first step. The net reaction, you can see water and CO2 in, solar energy in, oxygen out, and zinc gas out. But these two gases are being produced in different steps, in different processes, eliminating the need for high temperature gas separation. One attractive metal oxide system is the zinc oxide zinc redox. In the first step, zinc oxide is thermally reduced into metallic zinc. This reaction is highly endothermic and proceeds at temperatures around the 1700 degrees Celsius. The zinc then is sent to the second step where it reacts with water and CO2 to give hydrogen and CO, and the zinc oxide is recycled to the first step. Let's look at the maximum possible efficiency for converting solar energy into the chemical energy of the fuel produced. To do this calculation, we use this type of diagram that contains a solar reactor operating at the 2000 K, a quenching device, by the way, the solar reactor dissociating zinc oxide into zinc and oxygen, a quenching device to cool down the products of the reactor. Here I'm showing the hydrolyzer where zinc reacts with water to give hydrogen. Hydrogen is sent to an ideal fuel cell. This device extracts the maximum work that is possible from hydrogen as it recombines with oxygen to give water. So the work output of the ideal fuel cell is nothing else than the delta G of hydrogen plus oxygen to give water. And then the zinc oxide is sent back to the solar reactor to close the material cycle. So the efficiency of this process is going to be the work output of the fuel cell divided by the solar power input, and I'm taking into account also radiation losses. And when I plug the numbers, I get 35% no heat recovery, and up to 58% if I recover the energy that is rejected by the quenching device, by cooling the products to ambient temperature, and by recovering the heat of this exothermic hydrolysis, zinc and water to give hydrogen and zinc oxide. Therefore, the ceiling for efficiency is high, the potential is high, and it is up to us to develop the technology that approaches these very high limits of efficiency. Let's look at the reactor technology, and we'll start with the zinc oxide dissociation. This is the schematic of the solar reactor that is being developed at ETH and PSI for the thermal dissociation of zinc oxide to metallic zinc at 2000 K. This is a rotating cavity lined with zinc oxide particles, and the zinc oxide is directly exposed to concentrated solar energy. This is a photograph of a 10 kilowatt prototype. This is before assembling. Here you see the front face with an opening to the cavity to let in concentrated solar energy. This is the cavity itself, well insulated, and in the rear part is the feeding of the reactant, zinc oxide, and the handling of the products, zinc that is obtained in the vapor phase and oxygen. The reactor was tested at the solar furnace and PSI. This is a video clip showing during testing. And when while this video clip is playing, let me show you some interesting measurement. I'm plotting here the zinc oxide temperature in Kelvin measured with a pyrometer as a function of time in seconds. As soon as I open the shutter of the solar furnace, the temperature of the zinc oxide jumps from ambient temperature to over 2000 K, and the reaction starts immediately. And this is the result of this direct irradiation, where we bring the energy directly to the reaction site where it's needed. Typical results, nominal temperature 2000 K. We are introducing 10 kilowatt of concentrated solar power with a peak concentration at the aperture of 5,800 suns. That means 5,800 kilowatt per square meter over the small aperture. By the way, the aperture is 6 centimeters in diameter, so we are putting 10 kilowatts over 6 centimeters opening. Here you see the mass flow rate of the zinc oxide. And when we collect the zinc downstream, we condense and collect, we see that the particles have a zinc content that varies between 50% up to 95%. So we are losing some of the zinc by reoxidation, these two recombine, and I'm losing the zinc back to zinc oxide. And the way to avoid this recombination is by quenching this mixture, by rapidly cooling. This is the schematic of a quenching device that we are introducing at the exit of the reactor to quench by injecting argon. So we are quenching by dilution. We inject argon annular and also perpendicular. And we have seen that if we cool at a rate of above 77,000 Kelvin per second, we are able to collect particles that have a zinc content above 70%. It's not yet, we still lose some zinc, but 70% is good enough to also to keep the cycle running. Part of the reactor development is the modeling of the reactor, in which we couple heat transfer with the chemical kinetics. Here you see the energy equation, coupling the rate of energy change given by the heat transfer rate and the chemical rate. And we have developed this model in 3 dimensions, and here you see the validation in terms of temperatures that have been measured in different locations, and also in terms of the measured and calculated zinc oxide dissociation. Now we are using this model to scale up now the reactor. We are scaling up to 100 kilowatt. Now we don't have a possibility to test our reactor at PSI in Switzerland, so we are going with our reactor to the facility in Odeio. Here you see the field of heliostat and a big, gigantic parabolic dish, and we are going to place our reactor here in this tower to test the 100 kilowatt. By the way, this facility delivers 1 megawatt, but we need 100 kilowatt to test our reactor. And here you see the cross-section of this 100 kilowatt reactor. To give you an idea now the dimensions, we are talking an aperture now that is 19 centimeters diameter. Here in the front is the quartz window, 48 centimeters diameter, and the cavity itself has a diameter of 58 centimeters. And by the way, this is the rotating mechanism and also the quenching device. And here in the back, in the rear, this is the feeding of the zinc oxide particles. We are now in the process of building the reactor, and we plan to test it this summer in June, July in Odeio in France. Let me now come to the second step. Zinc reacting with water and CO2. It is well known that when you expose a zinc particle to either water and CO2, it reacts very fast, but right away it creates a layer around the particle that stops further reaction. You see that as well, for example, in aluminum. Aluminum reacts very fast, but it creates a thin layer of aluminum oxide, and then oxidation stops. In order to overcome this problem, we decided to work with nanoparticles. Nanoparticles of a size that is comparable to this layer of zinc oxide that forms when it's exposed to the reacting gases. Here on top of the slide you see we call it the aerosol reactor concept, in which we mix, in this case I'm writing steam, but can be also CO2 and zinc vapor, rapidly quench to form the nanoparticles that react in situ to generate hydrogen and the zinc oxide particles. And we have realized this concept in a vertical tube with 2 furnaces. In the lower one, this is where we place the zinc sample, which is evaporated. We have a balance to monitor the weight loss and calculate the mass flow rate of zinc vapor. And then here at this location, we mix with steam, we quench. to form the nanoparticles that react as the nanoparticles and steam flow together through this reaction zone. Here downstream we collect the particles and we analyze the gases. This is a temperature profile of this reactor. Here position 0 would be over here, and the reactor is about 1 meter high. First we boil the zinc, that would be over here, and then we quench rapidly at a rate of 1 million per second, 1 million degrees per second, to form nanoparticles with a mean particle size of around 50 nanometers. These nanoparticles react in situ either with water or CO2. This is one of our best experimental results, where you see the zinc evaporation rate, which we measure here, and the hydrogen production rate, which we measure with the gas chromatograph. And if you take the ratio of the two, you get the conversion 90%. This is a continuous mode reactor. We are flowing zinc continuously and reacting with steam. And the residence time is less than 0.1 second, a very fast reaction. This is some of the nice properties of nanoparticles. Very good conditions for heat and mass transfer and for reaction kinetics because of the high specific surface area. These are all very good things, but there are some complications. Nanoparticles, they deposit everywhere, and we are having complications with zinc nanoparticles and zinc oxide nanoparticles depositing along the reactor and not able to collect them downstream. So these days we are trying to solve this type of process technology problem because we would like to scale up the process, and we cannot afford having deposition of these particles in the reactor. This is an example of a run in which we are feeding CO2 instead of water. So we are splitting CO2. Here you see the CO2 reacting, the CO forming, and this is the zinc evaporation rate. Let me come back to the schematic of the redox cycle. And I would like to review very briefly the work that is being done in other labs with respect of this thermochemical cycle. Here on the corner you see the solar reactor that is being developed at DLR. They are using a cycle which is based on zinc ferrites, so it's reduction and oxidation, and the material, the reactive material is zinc ferrite, and they use two monolith reactors, one next to each other. While one is undergoing the hydrolysis, you see the steam reacting. This is the oxidation step. The other one is undergoing the reduction. And then once this is done, you switch the flows. Then you will have reduction here and oxidation here. And of course there is a temperature cycle, because the reduction is at higher temperature, the oxidation is at lower temperature. This one here on the right corner is the reactor being developed at the Sandia National Labs. This is a rotating disk. They are using cobalt ferrites as the active material, again undergoing reduction oxidation. On the top, they perform the reduction with solar energy, and here you see the oxygen being set free. And on the bottom, they flow CO2 or steam to do the oxidation and produce the fuel. And this disk is rotating. So you are doing both reactions in the same reactor. And one interesting feature of this reactor is that you can recover the sensible heat between the two temperature levels. This is the high temperature, this is the low temperature, and the sensible heat is recovered as the disk. They rotate they rotate in opposite directions. This is the fluidized bed being developed in the group of Kodama in Japan. They use nickel ferrites. This is a cavity reactor developed by the group of Al Weimer at the University of Colorado, also with nickel ferrite, so a cavity containing an array of tubes that are packed with nickel ferrites. And this is the reactor that is being studied in CNRS, in Odeyo. They have the reactants directly exposed to solar energy. They are studying the cycle, the zinc oxide cycle, as we do in Switzerland, and also the tin oxide cycle. Now, as I look at these 4 examples, we are talking about systems that we call them non-volatile systems. This is because when you do the reduction, the metal oxide stays in the same phase. You start with a solid and you end up with a solid. In contrast to the zinc oxide and tin oxide, because there you start with a solid and you go into the gas phase. It's a reduction and sublimation at the same time. So it would be zinc oxide to zinc vapor, or tin oxide to tin monoxide in the vapor phase. And of course there are advantages and disadvantages regarding non-volatiles and volatile systems. But let me show you an example of a non-volatile system, and this is the case of using cerium oxide, ceria. So in the first step, cerium oxide is dissociated. This is a non-stoichiometric cerium oxide with a lower valence, and oxygen is set free. And then in the second step, the ceria, the reduced ceria, is reacted with water and CO2 to produce the syngas. This is a system that we studied in collaboration with the Caltech in California Institute of Technology. And this is the reactor that we have developed. The main component is a cavity. You see it here with a small opening. We call it the aperture, to let in concentrated solar energy. This cavity contains a porous cylinder of ceria. We call it RPC, reticulate porous ceramic. And this porous area is directly exposed to the concentrated radiation to have a very efficient means of heat transfer, again, directly to the reaction site. During the reduction, we heat the cavity to 1600 degrees Celsius, and oxygen is set free. This is the reduction step in blue arrows. After the ceria is reduced, we cool down to 900 degrees Celsius, and then we flow water and CO2 radially, that the flows, they flow across the cerium oxide in the radial direction, and then we have the fuel, hydrogen and CO, exiting through this axial outlet. And this is in red arrows. We have tested this reactor at PSI. We used we call it the high-flux solar simulator. This is a facility that very similar to a solar furnace. It helps us simulate concentrated solar energy, the same heat transfer characteristics that you'd have on top of a solar tower. And here you see the schematic of the setup where we are feeding the reactants, getting the products and analyzing them. Now, here you see the results of the experiments. On the left side is the CO2 splitting. The lower curve is showing the temperatures of 4 cycles, 4 consecutive cycles. A reduction at around 1600 Celsius, oxidation at around 900 degrees Celsius. And then again reduction, oxidation, reduction, oxidation. And on the top graph, you see the composition of the gases at the outlet. Here, we analyze the gases by gas chromatograph. And here you see during the reduction, the oxygen peak. During the oxidation, CO2 to CO, the CO peak. And then again, oxygen, CO, oxygen, CO, oxygen, CO. 4 times. We did the same with water splitting. Instead of feeding CO2, Now we are feeding steam. Again, the temperatures, and here is the oxygen peak, here is the hydrogen peak, oxygen, hydrogen. Now we integrate the curves of oxygen, we integrate the curves for CO, we take the ratio between the two, we find 1/2. This is correct because when you split CO2, you get 1/2 mole of oxygen and 1 mole of CO. The same here, we integrate the curve of oxygen, we integrate the curves for hydrogen, we take the ratio between the two, we get 1/2. Correct, we are closing the material cycle. We know how much energy is going to the reactor. We can measure it. This is in the previous slide. We measure the energy that's going in optically with a Lambertian target and a CCD camera. In fact, I forgot to mention, this is a 3 kilowatt reactor. We are putting 3 kilowatts through a small opening, through the aperture. So now we can calculate the efficiency from solar energy to the chemical energy in the fuel. This is the way we define efficiency, is the heating value of the fuel produced, either CO or hydrogen. And in the denominator, we put the solar energy input, this 3 kilowatt, but integrated over the whole period of the experiment. And we are also putting the penalty of energy for using inner gas, because perhaps you have noticed that during the reduction, we are using a purge gas, we are using argon. And this argon comes together with oxygen, we have to separate it and recycle back. And this is an energy penalty. In fact, we are taking a typical value of 20 kilojoules per mole of argon separated. This is using conventional PSA membranes. And this comes also into the denominator. These are the values that we obtain. 0.8%, that is 0.008, so that you don't get confused. It's not 80, but 0.8%, and 0.7%. So very low values. However, for CO2, this is a world record. For the complete solar to CO2 splitting. For water splitting, I won't say that because you can always produce electricity, solar electricity with PV or solar thermal, and then run an electrolysis, and of course you will get already values approaching the 10%. So we still are very low values, but there is plenty of room for optimization, and our calculations indicate that we should be able to reach efficiencies approaching the 15%. This is feasible. We have been using a reactor that has not been optimized. This is a simultaneous run where we are feeding, this is a run when we are simultaneously feeding CO2 and water. And here you see the reduction step. By the way, here is the temperature, 1600 during reduction, and then around 1000 degrees Celsius, 1000 degrees Kelvin during the oxidation. And here you see the oxygen peak, and here you see the hydrogen and CO peak. We are splitting CO2 and CO simultaneously. And very interesting, when we vary, this graph is showing the quality of the syngas in terms of ratio of hydrogen to CO as a function of the stoichiometry of the reacting gas, water to CO2. We can control the amount of water and CO2 that we feed to adjust the quality of the syngas. For example, if we want to do Fischer-Tropsch to diesel, we would need a quality of the syngas 2:1 hydrogen to CO. Therefore, we would come to this graph and we see that if we use, for example, water to CO2 to 7, we will end up with the desired quality of the syngas. So we can go out of the reactor with the syngas mixture directly to the Fischer-Tropsch process for liquid fuels. The same would be for methanol. You need 2:1. And this is a very recent result. Was obtained in the lab about a week ago, we have here 10 consecutive cycles where we are simultaneously splitting CO2 and water. So here the lower curve is showing you the temperature in 2 locations. Again, reduction, oxidation. And here you see in red is the oxygen peak of the 10 cycles, and in blue and green, this is the syngas production, the solar syngas production, 10 consecutive cycles. I mentioned just a moment ago that there is still plenty of room for optimization. So what should we do to optimize? First of all, the RPC, the ceramic material that we put inside the cylinder, we didn't do any optimization. We just made this ceramic in the lab and place it inside the cavity. But there is a way to optimize the material, and this is the way we are proceeding. This is a photograph of the RPC, the porous ceramic material. We can run a computer tomograph to get the exact 3D geometry of the material. And then we can attach a computational grid. And by having this grid, we can right away calculate the morphology of the material, for example, the pore diameter, the porosity of the specific surface area. But we can do more than that. We can calculate the transport properties of this material. Very important is that we are exposing the material to concentrated solar energy. You recall we have the cylinder with the porous ceramics area, and we bring concentrated radiation directly on the RPC. And we want to understand how radiation penetrates and heats up this material to, for example, to understand what is the influence of the pore size, what should be the thickness of the material, and parameters of this type. So the way to do it is we solve the equation of radiative transfer that is giving three contributions. A negative contribution, this is radiation being attenuated by absorption and scattering, and then 2 positive contributions by internal emission because the RPC is hot, and by incoming scattering. Now, to solve this equation tells you how radiation travels as it penetrates into the RPC. We need to know the properties of the material, specifically the extinction coefficient and the scattering phase function, which we can calculate because we have the 3D representation. We can do ray tracing at the pore level and plot the probability of attenuation as a function of the path. Here is normalized to the pore size. And the slope of the curve is nothing else than the extinction coefficient. We can do the same by plotting the probability of reflection in a given direction as a function of the cosine of this direction. And this is nothing else than the scattering phase function. So we can proceed and solve this equation numerically at the pore level and understand how radiation travels through the material. We can also calculate the fluid transport properties. Here we are solving the Navier-Stokes equations, again at the pore level, because we have the exact geometry. And we can plot the pressure drop, non-dimensional, as a function of Reynolds. And then fit Darcy's law to get the permeability and the Froheimer coefficient, to understand how the gases, they permeate, they flow across the RPC. Another important property is the heat transfer coefficient, the convective heat transfer coefficient, and here you have Nusselt versus Reynolds, and we have derived a correlation for calculating these properties. And now that we have these transport properties, we can now go and custom design our RPC so that it will give us the best results. And this is the step that we are trying to design the most, what we believe is going to be the most optimal geometry for the porous ceramic material. I have a few minutes to go, and I would like to come now to the issue of closing the material cycle. You remember my first slide, I was putting a lot of emphasis on closing the material cycle. So the question is, from where is going to come the CO2? And the only way that we can close the material cycle is when CO2 is directly captured from air. And I'm going to show you an example how we can do that. The example is about running the reversible reaction of carbonation of calcium oxide to calcium carbonate, and the reverse reaction, which is called the calcination, from calcium carbonate back to calcium oxide. And this is the way we do that. We have one single reactor with a fluidized bed of calcium oxide particles. And we are first feeding atmospheric air through this fluidized bed, and we are heating the fluidized bed to 390 degrees Celsius. As we do that, the calcium oxide reacts with the CO2 that is very diluted in air. We have only 390 ppm of CO2 in air. Calcium oxide reacts with CO2 to give calcium oxide, calcium carbonate particles. And the air that is leaving the reactor should be CO2 depleted air, because we have extracted the CO2. And now we stop the flow of air, we heat to 850 degrees Celsius, and we drive the reverse reaction, the calcination. Now the calcium carbonate particles are decomposing, giving the original calcium oxide particles, and a pure stream of CO2 is leaving the top of the reactor. This is an example of an experimental run in the lab where we ran 5 cycles. And what you see here is the CO, first of all, the red curve that you see here, this is the temperature here on the right side in degrees Celsius. So we are running carbonation at about 400 degrees Celsius, 390 degrees Celsius, and the calcination at about 850 degrees Celsius. And then the blue curve that is here measuring in the left axis is the concentration of CO2 at the exit here. And the way we measure, we are using an IR infrared detector with an accuracy of 1 ppm. We can measure the concentration of CO2. So we start with the first carbonation and we measure 0. That means we are stripping all the CO2 out of the air, and the air that is being introduced has a concentration of CO2 of 390 ppm. Very fast reaction. Residence time is less than 0.1 second. It's a 2 centimeter tube with a fluidized bed about 15 centimeters high. After a while, I think after 20 minutes, we stop, and now we are heating to 850 degrees Celsius, and here is the curve for pure CO2. And we repeat that 5 times. Now we integrate these blue curves, and we divide by the CO2 that we capture during the carbonation. We take the ratio of the two, and we get 99%. So we are closing the material cycle. So that would be a way of doing it. Very nice results. We publish also a few papers in some journals. However, we are not happy at all. We have decided to stop. And this is the reason. For the carbonation step, we need to heat to 390 degrees Celsius. Now, remember, we have 390 ppm of CO2 in the air. That means for every mole of CO2 that we want to capture, we need to heat 2,000 moles of air. It makes the whole process not feasible. We cannot even afford heating the air even 10 degrees. We did a calculation, we look at the economics of the process, the feasibility. We cannot afford even heating the air 10 degrees. So this is not going to work. Although it works in the lab, it has basically zero chances of becoming an economically feasible process because of the huge amount of energy that you need to bring the air to the temperature level to capture only 1 mole of CO2. Any process that is feasible will have to have a carbonation step that occurs at ambient temperature and with very low pressure drop. We cannot even afford, we did the calculation, more than 100 millibars, the pumping work, it already makes the process non-feasible. So it has to be a very passive process, perhaps with the wind brings the air, or a small ventilator that you take over a pressure drop of up to 100 millibars, taking place at ambient temperature. So we have changed completely our approach, and now we are using a material that is based on amine functionalized silica gel. The absorption takes place at 25 degrees Celsius in 1 bar. And then we desorb at about 90 degrees Celsius. We have to pull a slight vacuum to make the reaction go. And here is an example of 40 cycles with this material, where we show the stability of the material, but we still need to improve the capacity. You see, we are now capturing about 0.2 millimole per gram. We want to bring this number at least to 1 millimole per gram, so that we don't need to use a lot of material to capture every gram of CO2. So this is the work that these days we are developing. And now I come to my favorite slide, because now I can tell you the story. Now it's a complete story, and it's a complete perfect material cycle. For example, we may start here from the left. I bring atmospheric air, and through an absorption-desorption process, I can obtain pure CO2. And here is an outlet for CO2 depleted air. Air without CO2, I release back to the atmosphere. Then through the redox process, the reduction oxidation, either with zinc or ceria or ferrites, you can convert CO2 and water to the syngas mixture. This mixture, we like it very much, hydrogen and CO, because this is the path to liquid fuels through conventional Fischer-Tropsch or other catalytic process. With these liquid fuels, we can fuel our cars, we can fuel our airplanes, and as we use them, we will emitting CO2 and water. Nature takes care of recycling the water, and we also take care of recycling the CO2. Very interesting that also we discovered a few weeks ago is as we do this process of absorption and desorption to collect pure CO2, we are at the same time collecting pure water. Even if we use dry air with a humidity of 0.3%, we still have 10 times more water content than CO2 content. And when we do this process and we do the desorption, we obtain a mixture of CO2 and steam. We condense the steam, we have pure water. Very interesting, because if we want to have this process, for example, in the desert of Andalusia, there water is a problem. We will place this plant next to the solar plant. This is concentrated solar energy. This is perhaps with flat plate collectors. And the CO2 capture plant will deliver both CO2 and water to the solar concentrating plant to produce the syngas. And the material cycle is perfectly closed. This is my group at ETH and PSI. This is the group of doctoral students and postdocs. And of course, the things that I presented today, many of the guys here are the ones who are working hard and deserve the credit. Thank you for your attention, and I'll be happy to answer questions now.
¿Uno de los miembros de tu grupo está ahí?
Dominic. Hi, Dominic.
Muy bien, pues muchas gracias, Aldo, y la verdad es que yo creo que espero que os haya gustado. Y bueno, la verdad es que incluso veo que nos ha dado datos de hace muy poquitas semanas, ¿no? Con muchos ciclos, y como podéis ver es una línea que está todavía claramente en desarrollo, en germinación, pero muy prometedora. Y como cualquier actividad de desarrollo científico y tecnológico, pues cada vez que bueno, resuelves un problema, pues probablemente se presentan 3 o 4 problemas más. Bueno, yo, si os parece, pues ya os doy la oportunidad de hacer todas las preguntas que consideréis necesarias.
En español también.
Sí, en español, por supuesto. A ver, profesor Calleja. Veteranía es un grado.
Guillermo Calleja, de la Universidad de Juan Carlos. ¿En Spanish o English?
Como usted prefiere.
Bueno, algunos comentarios y alguna pregunta o sugerencia incluso. Era obvio que no iba a ser posible el proceso de carbonatación, calcinación del aire, del CO2 del aire, porque es que el aire además tiene anhídrido sulfuroso, gases, óxidos de azufre. Por poco que sea, a la larga se combinarían rápidamente con el óxido de calcio, dando sulfato cálcico, que no es tan reversible la reacción como la del carbonato. Por lo tanto, consumiría el óxido de calcio poco a poco, lentamente, hasta reducir la eficiencia del proceso. Es decir, que aunque le salieran las cuentas bien, a la larga tendría que ser un aire muy limpio de óxidos de azufre. Si no, bueno, ese era un comentario. El otro comentario también, han probado, pregunta, cuando estaba hablando de evitar que las partículas de zinc se queden adheridas en el reactor tubular, en la pared del reactor tubular durante la producción de hidrógeno, las nanopartículas de zinc, ¿han pensado en la posibilidad de inyectar argón a través de las paredes permeables, paredes que permitan un flujo hacia el interior, un pequeño flujo de argón que evitaría la deposición de las partículas? Esta técnica se hace en otras finalidades, pero a lo mejor aquí era viable.
Primero, su segunda pregunta. Nosotros no hemos intentado, pero en el grupo de Weimar en Colorado, ellos utilizan un reactor que tiene porous walls and they inject argon under pressure to prevent particles deposition. And they have some kind of mixed results. Sometimes it works, sometimes not. We haven't tried. We just took a quartz vertical reactor. And that may be a way to go to avoid deposition of particles. Now, if I may come to your first comment. We are aware that there are several groups studying the calcium carbonate, the carbonation calcination for capturing CO2 from flue gases. For example, the work of the group of Abanades. They have published tons of material in all kinds of things. However, they use flue gases. Flue gases from the combustion of coal, where you have major content of sulfur. We are using air, and we have done only 5 cycles. And to demonstrate that there is no that can be recycled, we will have to do 1,000. But we will not do that because we don't believe that the calcination, carbonation is the way to go. But having said that, I don't know what is the sulfur content in ambient air, and I don't know how much is going to affect the reaction. I will, yeah.
One more, last one. Last one. Usted dijo que la eficiencia en producción de hidrógeno en su reactor solar de simulación, que no estaba optimizado, era de un 0,7%, pero que cuando se optimiza un reactor se puede llegar a un 15%.
Sí.
¿Cómo van a hacer eso? Porque no estamos hablando de un orden de magnitud, es el doble de un orden de magnitud, de 0,7 a 15 es casi 20 veces más. ¿Cómo van a hacer eso?
Tengo que poner el slide del reactor para mostrarle cuáles son los sources of heat losses. We are losing energy, two main sources. Let me see. Here it is. Two main sources, radiation losses through the aperture and conduction losses through the walls. And conduction losses, we will have to, for example, improve our insulation. Radiation losses, we will have to make the cavity more black absorber and perhaps improve here the CPC. This is a secondary concentrate. To make this aperture smaller, because the losses go with the temperature to the fourth power. No? This is one way we want to proceed. The other thing is the material that we are using basically is not optimized for the flows that we are using. We are putting too much excess. We are feeding too much water and CO2. We will have to match the flows to the material that we have, and depends on the kinetics, and to the rate of heat transfer. So basically two things. Improve the reactor so that the heat losses are reduced, and match the Syria to the flows of the reacting gas and to the rate of heat transfer. When we do these calculations, assuming everything looks pink, no? Everything looks perfectly, then we obtain a ceiling, a maximum efficiency that is 20%. This is why I say that should be feasible to reach the 15%.
¿Se podría llegar a eliminar el argón?
And the argon, to eliminate the argon, we will have to go to higher temperatures. For example, 1700 degrees Celsius. And then we don't need anymore to recycle the argon. But 700, we are already reaching the limit of what the Syria can do. As we go to 1700 degrees Celsius, we lose Syria metal in the vapor phase. Cerium metal, sorry, in the vapor phase. So we are just reaching the limit of the temperatures that we can operate.
Yo quería preguntarle por qué utilizar para utilicéis para capturar el CO2 los ciclos de carbonatación y calcinación, ¿no? ¿Por qué no utilizar directamente el carbonato formado en el ciclo termoquímico en vez de tener que recuperar el CO2 para utilizarlo en el ciclo, sino, o sea, capturar CO2 en carbonato y luego el carbonato utilizarlo en el ciclo?
Bueno, el ciclo termoquímico es el ciclo de redox, reduction and oxidation. ¿Y tú qué propones? ¿Mezclar el calcium carbonate con el metal oxide? ¿Eso es lo que propones? Entiendo. Pero luego, no está bien, ¿no? Para la reacción de reduction, sí. Podrías poner calcium carbonate, for example, with zinc oxide. Sorry, calcium carbonate with zinc. And then as you heat up, the CO2 will be released and reacted with the zinc. You will produce CO, but you will end up with a mixture of zinc oxide and calcium oxide. ¿Me sigues? Sí, pero luego ¿cómo haces? Porque yo utilizo el calcium carbonate para capturar el CO2 del aire y hago las partículas de calcium carbonate. Y lo que tú propones es el calcium carbonate mezclarlo con el redox system, ¿cierto?
Hay un ciclo de la fruta de manganeso con carbonato de sodio que hace una reacción, la fruta de manganeso con el carbonato de sodio y agua, producen un óxido de sodio, manganeso y hierro e hidrógeno en la misma reacción, y luego ese óxido de manganeso con el CO2 recuperan la ferrita inicial y el carbonato. Sí. Y sería una forma de eliminar pues esa etapa, ¿no?, de descarbonatación. No sé, hay un ciclo que es ese. Sí. Creo que lo han hecho Albani creo que se llama.
Y luego puedes recuperar, con ese ciclo puedes tomar el CO2 del aire.
Sí, ellos han demostrado que sí.
Bueno, muy bien, ¿no?
y recuperar el
Lo
carbonato de
tienes que
sodio.
mostrar. Ah, bueno. Ideas mejor de lo que yo. Mejor.
No es un ciclo que ya está muy
Sí.
estudiado.
Lo que hay que siempre fijarse que es un closed material cycle, ¿eh?
Claro,
Mucha gente viene con ideas muy entretenidas, pero al final no se puede cerrar el ciclo de materiales. Entonces ya no sirve.
Hombre, la eficiencia también es muy baja. O sea, no tiene mucha eficiencia en hidrógeno, pero sí que la ha usado.
Buena idea, ¿eh? Trabaja en idea. A ver, ¿alguien más? A ver, la universidad, ¿quieren algo?
Aldo,
Hola.
Juan Ángel de la Universidad de Juan Carlos. Primero felicitarte por la conferencia, una conferencia magnífica desde el punto de vista científico y académico. Y un par de curiosidades, principalmente relacionadas con el óxido de cerio. Una va relacionada con la posibilidad de ciclado y luego con la caracterización de la espuma. Lo que has comentado, de hecho, creo que la transparencia, la siguiente o dos después, aparecen unos datos de superficie específica.
La espuma, esta.
Sí, la espuma cerámica. Si vuelves,
Sí.
aparece ahí un dato de superficie específica que no he llegado a interpretar, vamos, aparece como unos milímetros a la menos, no he entendido cómo está expresado. Ahí. Superficie específica.
Espera, esto es el área dividido volumen. El área dividido el volumen. Te dice cuánto, como la reacción con agua el CO2 es surface reaction. Tú quieres tener un valor muy alto acá. Increase the specific surface area. No es volumen. Sí.
Con respecto al ciclado, en el caso del material de cerio, vamos, el óxido de cerio, a medida que vas ciclando y vas sometiendo al material a esas temperaturas, en diferentes niveles, estamos hablando, creo recordar, la etapa de reducción en torno a 1600 grados centígrados, la etapa de sí, lo que sería la hidrólisis, y luego ya estaríamos hablando de 900, 800, 900. ¿Se mantiene la superficie específica del material o se va amorfizando el material y va perdiendo superficie?
Bueno, esto es lo que tiene interesante Siria, que mantiene la estructura del cristal. El cristal se mantiene. Pero, fíjate, este delta es muy pequeño, es 0.05. O sea, necesitas mucho material para producir 1 mole of oxygen o 1 mole of hydrogen and CO. Por un lado, mantiene la estructura de Siria, por eso se utiliza Siria mucho para fuel cells, como oxygen conductor. Y eso es una ventaja. La desventaja es el too small of a delta. So there is no winner. You can always find whatever cycle you take, ferrite, Siria, zinc, tin oxide. People have done a lot of work. There are always advantages and disadvantages. I haven't seen any cycle that only has benefits. Yeah.
El soporte del material es silicon carbide.
No, es pure Siria.
Es pure Siria.
Siria, yeah. Because
Y
Siria
después
reacts.
de esos 10 ciclos sigue estando.
Sí, hicimos máximo 23 ciclos en el with the solar reactor y 500 ciclos en el laboratorio.
Y el material sigue manteniendo
Porque es muy pequeño el óxido que da, se mantiene en Siria cuando utilizas Siria puro. Mucha gente ha tratado de hacer el doping de Siria. El grupo de Gilles Flamand, hay otros grupos at Sandia Labs, they are doping the Siria to see if you can lower the temperature, make things go better. But then the Siria reacts with the support or with the doping. For example, Siria doped with iron, it reacts, or with other materials. So it's tricky with Siria.
¿Alguna pregunta más?
Elisa, sí.
Sí, yo quería hacer una pregunta bastante general, pero me gustaría saber su opinión en este sentido. Cuando hablamos de la potencia de un reactor solar, exactamente, quiero decir, porque, por ejemplo, ese reactor que he mostrado es un reactor de 3 kilovatios, pero nos estamos refiriendo a la potencia de la apertura del reactor, pero en realidad eso varía en función del horno o del simulador que tú utilices. Entonces, ¿cómo se evalúa realmente la escala de un reactor solar?
Bueno, el reactor está diseñado para 3 kilowatts. Este reactor 3 kilowatts. O sea, hemos hecho el diseño para meter 3 kilowatts. Entonces, cuando lo ensayamos en el horno solar o en el Solar Simulator, ponemos 3 kilowatts. Ponemos en realidad 3 kilowatts con el window, taking into account window transmission and reflection. So a little bit more than 3 kilowatts, perhaps 3.2 kilowatts. So we had 3 kilowatts going into the cabin.
O sea, tu pregunta a lo mejor, Elisa, es ¿cómo determina el flujo?
No, sino...
Flux.
Medimos el flux.
Sí,
O sea,
¿cómo ese diseño se hace para 3 kilovatios? O sea, simplemente depende del tamaño y de la geometría del reactor, evaluando las pérdidas que pueda tener. O, quiero decir, si ese reactor se somete a un horno mayor que pueda proporcionar más
si
potencia,
pongo más de 3 kilowatts, I'm overheating the reactor. Probably I will start melting. And if I put less than 3 kilowatts, perhaps I don't reach the temperatures that I need. No reaction. The design point is 3 kilowatts. And the way to do it is you measure the flux distribution at the focal point. You will get a Gaussian usually because you don't optical imperfections. Yeah. So that will be like a concentration of power flux. That will be kilowatts per square meter, as a function of radius. And then you, for example, if I'm using 3, I don't know, an aperture, I don't remember the aperture size here. I believe it's 4 centimeters. So I take 4 centimeters, you integrate, you get 3 kilowatts here. Yeah.
En el reactor rotativo, ¿las partículas se mantienen en las paredes o precipitan?
En el reactor de zinc,
Sí.
en el de zinc, el que... No, sí, las partículas se introducen y por la fuerza centrifugal se van contra las paredes. Y así mantenemos el reactor perfectamente insulado con partículas. Las partículas protegen las paredes del reactor. Y la reacción es zinc oxide to zinc vapor, o sea, las partículas se decomposen en zinc vapor y el vapor se va para afuera.
¿Y cuál es la velocidad de giro?
60 RPM para el 10 kilowatts. Cuando sí, es una lavadora, es 60 vueltas por minuto. Pero cuando vamos al reactor más grande, del 100 kilowatts, va a ser menos, va a ser algo así como 25 RPM, porque el radio es más grande y la fuerza centrifugal is not rotating very fast. You have seen in the video clip.
Bueno, alguno de los jóvenes, alguna pregunta, ¿no os de vergüenza? Una pregunta aunque sea más, ¿no?
No he escuchado preguntas sobre economía. Pensé que me iban a bombardear con preguntas en la escuela de...
Bueno, ¿no hay ninguna pregunta más? Víctor.
Yo sí, pero no lo conozco. Ya sí que conozco,
¿No?
Víctor de la película. No por email, pero no lo conocemos.
Raúl. Tampoco. Bueno, pues la verdad es que si no, yo os espero que os haya gustado. Yo creo que, como veis, deciros que parte de este trabajo, como lo veis ahí abajo a la derecha, acaba de ser publicado hace muy poco en la revista Science. O sea que, como podéis imaginar, es una investigación todavía, aparte de muy prestigiosa, pues muy novedosa todo. Entonces, bueno, pues esperemos que algún día, ¿no?, sea realidad. Pues muchas gracias, Aldo.
Ya, muchas gracias.